Thank you, Dr. Weglein, and good morning. Thank you for coming to my talk. And in this talk, I'm going to show you the first test and the evaluation of the inverse scattering series internal multiple attenuation algorithm for an attenuated medium. As shown in this schematic diagram, our objective is to remove the internal multiple from the data. And if the subsurface world is acoustic or elastic, just as all the previous synthetic data tests have involved, the current ISS attenuator can predict the internal multiple with the perfect time and the approximate amplitude. Referring to Coates and Weglein in 1996, they gave the first test of ISS attenuator working on the elastic medium and showing it can give the impressive prediction result. So now, what about the inelastic medium? We know the high frequency energy will be attenuated and the velocity will be dispersive. So actually, the real subsurface rocks are always inelastic. And in some exploration areas, for example, for the pre-salt place in deepwater Gulf of Mexico, the offshore Brazil, and the central North Sea, the inelastic property will be more significant. So under this situation, we may want to know, in this inelastic media or in this more realistic world, can the current ISS attenuator predict the internal multiple with the perfect time and approximate amplitude without any information of the absorptive and dispersive properties? If so, this method can be shown more reliable. And in this talk, I'm going to examine this. Before the analytic and the numerical examination of this algorithm, I'd like to first remind you how to express the wave field. For the acoustic or elastic media, we can use this one-dimensional wave equation to express the wave field, say the pressure P, and assuming one-way wave, P of x omega is equal to E of I omega over C0x. And for the inelastic media, assuming the constant Q model, which is first proposed by Pierre Canson in 1979, and we can use this one-dimensional wave equation to express the wave field. And from this equation, we have this frequency-dependent factor. It is constituted by two terms. The first term is related to the energy attenuation, since the imaginary I existing in this term. And the sine omega is used to guarantee the energy is attenuated in both positive and negative frequencies. And the second term is related to the phase delay because of the velocity dispersion. Here, the omega r is used as the reference frequency and could be chosen as the maximum frequency in the experiment. And here, the C0 is the velocity at this reference frequency. Q is the attenuating factor. Now, if we combine all these terms to give a new definition of C of omega, which is the frequency-dependent velocity, and again, if we assume the one-way wave, we can express the wave field P of x omega by using this expression, E of I omega over C of omega x, the same general form as the previous acoustic case, right? However, please pay attention. This expression can be expanded in these three terms. And the first term is the phase term corresponding to the velocity at the reference frequency. And the second term is contributing to the energy attenuation. And the third term is contributing to the velocity dispersion. Now, if Q goes to infinity, the last two terms will go to 1, and only the first term is left. This is exactly the same form as the previous acoustic or elastic medium. So we can say if Q goes to infinity, the inelastic medium is going back to the elastic medium. After knowing how to express the wave field in the inelastic medium, I'd like to examine the ISS attenuation algorithm by using this two-reflector 1D model and assuming both the source and receiver are at depth 0. This is the depth of these two reflectors, and this is the parameters of this model. C is the velocity, rho is the density, whereas Q is the attenuating factor. And we use R1 and R2 to represent the reflection coefficients at these two interfaces respectively. And T12 and T21 are the transmission coefficients at the first interface. And we know there are two primaries in the data. So following the strategy given by Weglein et al. 23, we'd like to show you the workflow of testing ISS attenuator for data with Q. First, let's look at the data in the frequency domain, say D of omega. We know we have two primaries, and these are the analytic expression of these two primaries. For the first primary, we can see besides the reflection coefficients at the first interface, the first primary is also experiencing the absorption at the first layer. And for the second primary, we can see besides the transmission loss and the reflection coefficients, the second primary is experiencing the absorption in both the first and the second layer. So now we change the variables from omega to the wave number kz. We can get the B1 of kz. It is the summation of these two primaries in kz domain. And then we apply the Fourier transform over kz to the pseudo-depth domain, say z, and we can get the B1 of z. It is the summation of these two primaries in the pseudo-depth domain. After obtaining the B1z, we can apply the ISS attenuation algorithm by substituting the B1z into this integral formula. And I'd like to use this cartoon to show you how it works. And we can see there are three events existing here. They are corresponding to the three B1z in this integral formula. And here the epsilon is used to make sure these three events satisfying the deeper shallower and deeper relationship. And we know that there are two primaries existing in B1z. So now if we assume these two primaries are isolated, and we can choose the reasonable epsilon to make sure there are no overlap during this integral. After a series of calculation, we can get the analytic expression of the predicted internal multiple B3 in the KZ domain, pretty complex forms. And I just involved this detail in my annual report, and we will go back to this later. And in this two-reflect model, just as the way we express the wave field of two primaries, we can also give the analytic form of the actual internal multiple. Looking at this formula, you can see the Q1, Q2, and Fk are existing in this formula. So the actual internal multiple is also experiencing the absorption in the first and the second layer. By comparison these two formulas, we can get the relation between the predicted internal multiple B3 and the actual internal multiple Rm, showing like this for data with Q. Later we will use the numerical result to show that this prediction result can give you the perfect time and approximate amplitude. And looking at this relation, we can see there's one multiplication term of these transmission and reflection coefficients. There's also another exponential term related to the energy attenuation. And let's consider the meaning of this relationship. When Q goes to infinity, say there's the model is the elastic, then all these reflection or transmission coefficients become the real value. Then this term goes to 1, and Q goes to infinity, so this term also goes to 1. Then we can get the relationship between the B3 and Rm, showing as this. So only the multiplication term is left in this relationship. So what's the physical meaning between these different relationships with and without Q? So for data without Q, say in the elastic medium, from the Dr. Weglein's tutorial and the previous presentation in this morning, we know that the transmission loss on and above the internal multiple generator will be overestimated by using this ISS attenuator. And as I using this model, this is the model I used in this example. So the internal multiple is generated at the first interface. So the transmission loss is only the transmission loss at the first interface will be overestimated. And for the elastic medium, we just use the transmission loss to represent the energy loss for the wave pass through the interface. So it is only corresponding to the transmission coefficients. Now, for the model with Q, say the inelastic medium, we'd like to expand the transmission loss to a more general definition. Say it is called accommodating the energy loss for accommodating the energy loss for both at the interface and in the layer. So in terms of the statement that the transmission loss on and above the internal multiple generator will be overestimated by using the ISS attenuator, we know that not only the transmission loss at the interface, which is the first interface in this example, will be overestimated. The transmission loss in the first layer will also be overestimated. So that's the exact reason why in this relationship there's an astral exponential or decaying term. This term is exact corresponding to the energy loss in the first layer. Hope this explanation can help you to understand this relationship result. And next, I'd like to use two models to further numerically evaluate this algorithm. And for both examples, I will still use a two reflector model. And we will know in the data there will have two primaries and one first order internal multiple. And these are the parameters we use for the first model. And for the Q, we use 100, 100, and 80 for the first model. Let's look at the result. The blue line is used to represent the input data. We can see the first primary, the second primary, and the first order internal multiple. And the red dashed line is used to represent the internal multiple prediction. We can see it matches well with the actual internal multiple. Extracting the actual internal multiple and the prediction for further comparison, we can say the prediction gives the perfect time and approximate amplitude. And for the second model, we keep everything unchanged except we decrease the Q value of the second layer to be 20. It's a pretty small value. So we can imagine both the second primary and the internal multiple will experience a strong absorption with this small Q value. And we can see from this figure showing as the blue line, the second primary and the internal multiple, the amplitude is very small and the phase is delayed. However, the prediction result is satisfying. Say the prediction time is correct and the amplitude is approximate. So until now, I've shown you the analytic and numerical result, numerical evaluation. So given the constant Q model, we know for this unelastic medium, we know that the ISS attenuator can predict the internal multiple with the perfect time and approximate amplitude without any information of the absorptive and dispersive characters. And more generally, we can say this ISS attenuator can perform well even without know the medium is elastic or unelastic. So this method is model type independent. This is exact the statement given by Weglein et 23, and my work just further prove their statement. So now if you are considering the unelastic media and you just want internal multiple attenuation, you can be confident to use the code we provide in our website. And we have two versions. The first version is provided by Dr. Sam Kaplan, and the second version is provided by Dr. Paulo Trinki. And since we've been talking about the internal multiple elimination, so a reasonable question is how to eliminate the internal multiple for inelastic media. From the previous talk given by my colleague Yang Lizhou, we know that we already have an acoustic internal multiple elimination algorithm could be extended to the elastic media. So now we may want to know if there is a method to transform the data from the inelastic medium to the corresponding data from the elastic medium. The answer is yes, there is. The ISS Q compensation without the Q method can achieve this objective. And then here I'd like to use this numerical result given by Internet and Lero 2010 geophysics to show you how this ISS Q compensation without the Q method work. And clear to see the second primary, in the upper panel is attenuated because of the Q absorption. And after applying the ISS Q compensation method, it's effectively compensated. And this method is working on the primaries only. So now we have a strategy. We want to use the ISS attenuator as an initial step for the further internal multiple elimination. And here we have two suggestions to be recommended. The first is the ISS attenuator can map a bridge between the ISS Q compensation without the Q method and the ISS elastic internal multiple elimination. Since the ISS attenuator can predict the internal multiple with the perfect time and approximate amplitude, we can substitute the returned primary and the residual weak internal multiple into the ISS Q compensation method to get approximate primary and then step into the ISS elimination algorithm. And the second suggestion is we could eliminate the internal multiple by using higher order ISS inelastic series directly in the future. At the end, I want to thank my colleague for the help and cooperation. I also want to thank our sponsors for the encouragement and the support. Thank you. Thank you for your attention.